Good day, students. Let's start some more fun time. We're going to look at minimizing travel time. An island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying in a cabin on the shore that is 6 miles west of the point. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? And that's a little hard to come up with a picture with. It is there, but the first thing we can toy around with getting the parts that we want. This part here, an island is 2 miles due north of its closest point. That's representing this. I'm going to use a different color there. That's doing that. And then it says the total distance is 6 miles west of that point. So that's this right here. And now we know that the visitor runs a certain distance. He runs a certain way right here. That's not showing up. Maybe do blue. Runs a certain way along here and then swims. So we kind of need to come up with some variables. I called them X and Y. Well, the problem called them X and Y. And if this is X, then this has to be 6 minus X. And the way you can see that is if you just say, we're going to call this like an unknown. I'll put that like a question mark here. X plus question mark. That's not showing up. Let's do that one. X plus question mark has to equal 6. So subtract X from both sides. We get question mark equals 6 minus X. And that's how you get that right there. Now, we want to minimize the amount of time it takes. We have some information on speed. We've got a speed there and a speed there. So the formula for speed is distance over time, like miles per hour. And so if we solve for time, time equals distance over speed. So if we look at the run time is doing this distance. I want a different color. Is doing this distance over this amount of time, or this rate, or speed. So X over 8. And then the swim time is this distance over the swimming speed, which is 3. So Y over 3 will be our swim time. Our total time should be run time plus swim time. So we've got T equals X over 8 plus Y over 3. Now to proceed, we want one variable. So we need another equation. The other equation we're going to get is by making a big triangle out of that. We're going to look at this triangle to figure out what Y is in terms of X. Okay? So I redrew the triangle down here. Y is there, 2 is there, 6 minus X is on the bottom. Y squared equals 4 plus 6 minus X squared. We take the square root. Y is technically plus or minus, but we're doing a distance, so we can ignore the minus one. So we're going to take this thing for Y. We're going to stick it in right there. And I pulled the fractions out front to make it look like this. So 1/8 X plus 1/3 times the square root of 4 plus 6 minus X squared. All right, so X can be 0 if they don't, we need the domain. So X could be 0 if they started swimming right away, but they swim slower than they run, or the person could run the whole way, then swim. And so it could be the full 6. So X is going to go from 0 to 6. Those are our boundary conditions. So taking the derivative here, you make sure you go slowly. There's some chain rule shit going on. I end up getting 1/8 minus 6 minus x all over 3 times the square root of 4 plus 6 minus x squared. If I set that equal to 0 and solve, I got to here. Here I cross multiplied to get this. Rather than distribute, I just squared everything as is. And then here I did 9 times 4 to get 36. And I did 9 times 6 minus x squared to get that. I just distributed the 9. I didn't clean it up more than that because I saw 6 minus x squared on both sides. And I thought maybe I could make this shit easier if I didn't try to multiply everything out. This is something that you learn how to do with practice. Sometimes we would just want to multiply everything out, but this is going to give us big, ugly coefficients. This one would have a 64 times 36 as a number there when we do it. I don't want to do that math. I don't know about you, but I don't want to do it. So I'm not going to do it. So I distributed there. I subtracted 9 times 6 minus x squared from both sides. I got 36 equals 55 times 6 minus x squared. I divided by 55. And you'll notice that 6 minus x squared is the same thing. If I factor out a -1, I've got x minus 6. So I can do this. And that turns into this. But that equals 1. So 6 minus x squared is actually the same thing as x minus 6 squared. I like that because it's going to make doing some of the math a little bit easier. So at that point, I have x minus 6 squared equals 36 over 55. And I took the square root to get down to there. Okay. So when you take the square root, you get x minus 6 equals plus or minus square root of 36 over 55. This is the fully cleaned up form, but I think that's a pain in the ass to write, so I didn't write that for now. I used the plus or minus one. Then we got to add this 6 to both sides to get x by itself. When we do that, we get x equals 6 plus or minus 6 square root of 55. So now we split it up into our two versions, plus or minus. If I do the plus one, I don't know how much this is, but I know if I add 6 to it, it's definitely bigger than 6. So I don't want to use 6 plus. In fact, that is strictly greater than. So if I do the 6 minus gets us a value that looks like that. 5.19 miles. That's less than x equals 6. It's greater than 0. That looks like a valid bingo. We just got to check it. We got to check that in our boundary conditions. So we're going to use this value, and we're going to use 0, and we're going to use 6. Those are our critical points to check for the absolute minimum on time. So that was our time equation, and we start plugging shit in. X equals 0 does not zero out the problem. X equals 0 zeroes out that, but we've got 4 plus 6 squared. 4 plus 36 is 40. We got square root of 40 over 3, which ends up being approximately 2.108. If the person runs, that's if they swim directly. X equals 6 is if they run and then swim. And if we plug in x equals 6, we end up getting 17 over 12. That's approximately 1.417. And these are all in hours because it was miles per hour. That was the speed. And finally, we do our weird value here, plugging it in. You could throw it into a calculator right away. I tried to do some cleaning up real quick. I don't know why. When you plug it in, you get 1.368 hours. We were trying to minimize. The smallest value here is that one, which goes with that distance running. So when we write our equation, we're going to say that the person has to run 5.19 miles down and then start swimming from there. And the shortest time would be 1.368. I'm betting the person runs about 5 miles because they're not going to waste the time doing these calculations. They'll run until it looks like it might be shorter to just start swimming. Next example we have is maximizing revenue. A car rental company charges its customers P dollars per day, where the price is between $60 and $150. It is found that the number of cars rented per day can be modeled by a linear function. N equals 750 minus 5P. How much should the company charge each customer to maximize revenue? So we take a look at this, and revenue is normally it's just units sold times price. In this case, it's units rented times price. So the units rented were number of cars per day was N. Price was P. N times P. 750 minus 5P times P. We already have our conditions here. Our boundary conditions are listed. Maybe I'll write them down right there as a reminder. We take the derivative, we get 750 minus 10P. We set that equal to 0, and we find P equals $75. So we've got 3 values to check. We need to check $60, we need to check $150, and we need to check $75. We're going to check it in our revenue function to see which one maximizes. Okay? So we test 60, 50, and 75. If I plug in 60, it doesn't zero us out. You'll notice the revenue is $27,000. If we do 75, that's $28,125. If we do $150, that actually ends up being a 0. We did want to maximize though. This is the value we wanted that gets us the maximum value. That's when the price was $75. That's what was asked. How much did the company charge? So our answer is going to be that the company should be charged a rental price of $75. All right, one more. This one's kind of neat. Maximizing the area of an inscribed rectangle. A rectangle is to be inscribed in the ellipse x squared over 4 plus y squared equals 1. What should the dimensions of the rectangle be to maximize its area, and what is the maximum area? Okay. So we've got a picture here, and the area to be maximized is going to be length times width. So the easiest way to go about this, to relate length and width to our x and y, is that this length here is x, because it's a coordinate y, x, y here. This height here is y. So it looks like length, and since it's a rectangle, it's going to be even. That's x, and that's y and y. We get length equals 2x and w equals 2y. Now, if I plug those in as is, we've got area equals 2x times 2y. It's not down to one variable yet. So what I'm going to do is I'm going to solve this equation, my constraint equation, my ellipse that's constraining it. We're going to solve that for y. What I did is there's my equation. I thought it would be a little bit easier if I just cleared fractions. X squared plus 4y squared equals 4. I subtract x squared from both sides. I didn't divide by 4 because I didn't want to have a fraction in the square root. So I just took the square root right now. Take the square root right here, and you get 2y equals plus or minus, but the minus doesn't count, so we just have the positive one, okay? So 2y equals that, so y equals 1/2 4 minus x squared. I went and I plugged that in there, and I got my equation down here. Now, since we're working with x, I can see that my largest conditions on x are like doing the full length. So x can go from 0 to 2. So that gave me my conditions down here. 0 is less than or equal to x less than or equal to 2. Okay. So after cleaning up this problem a little bit, the 2 times the 1/2 clear out, and I had 2x times square root of 4 minus x squared. This is where we got to take the derivative. It's not pretty. It doesn't end up being too bad. The 2 here cancels the 1/2. And this moves to the bottom. So I should have a negative 2x squared on top. And on bottom, I have a square root of 4 minus x squared. So at this point, to get a common denominator, I'm going to multiply that one by square root of 4 minus x squared over square root of 4 minus x squared. I'm going to multiply that on that one right there. And you see what we get down below here. If I distribute, I get 8 minus 2x squared minus 2x squared gives me an 8 minus 4x squared on top. And we still got the square root of 4 minus x squared on bottom. Now we got a spot where the bottom can equal 0, so we need to take that into account. So we're looking, first off, we'll look at where the top equals 0. That gives me a prime equals 0. We solve for the x, and we get x equals plus or minus square root of 2. X was the distance on from 0. It was between 0 and 2. So the only one that worked was the positive square root version. If we solve for the denominator where it's undefined, it's the bottom equaling 0. And we get x equals plus or minus 2. Again, that's the positive 2. So we had 0 was a possible answer, square root of 2 was a possible answer, and 2 was a possible answer. These were boundaries. And that's right there. The occurrence of this bad boy right here says we got to cancel out that one. So we're going to test 0 and square root of 2. No, what am I doing? It doesn't mean we cancel it out. That's completely wrong. We're going to work with it, figure it out. So, and x equals 2. What was my equation? Oh, I got my equation down here. So if we do a equals 2x times square root of 4 minus x squared, x equaling 0 right away, we can see if we plug it in right there, that goes to 0. All right, let's take a look at our other option. If we do x equal our other boundary condition, I got a equals 2 times 2 times the square root of 4 minus 2 squared. 4 minus 4 is 0. This zeroes out again. A equals 0 on x equals 2. So when we do x equals square root of 2, this is being plugged in. We got x is there. We got square root of 2 squared is just 2. We plug those in. We got 2 root 2 times square root of 2. It ends up being 4 when you clean it up. So that will be our max area. Our max area is 4. And we had x. X is square root of 2. We knew that L was 2x and W was 2y. We plug in our x into those to find out what length and width are. So length should be 2 square root of 2. What kind of inches were we working in inches here? No, it doesn't even say the units. So undefined units here. So we've got 2 root 2 units for the length. We got square root of 2 units for the width. That does give us an area of 4 square units, whatever they are. And that'll be all the stuff in applied optimization. Now get up there and kill those equations.